In this video, we're going to look at the law of cosines. So we're going to use law of cosines if we're given a triangle with information of side, 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 or side, angle, side. So using law of cosines, we use this when we can't create a full fraction in law of sines, so we don't have an angle with its opposite side length. If you begin with law of cosines, you can complete the problem using law of cosines to avoid the ambiguous case. In other words, we're going to talk about this in example 2, but we can just keep using law of cosines rather than setting up law of sines. But we'll talk about that in our second example a little bit more. But our formulas for law of cosines, so given any triangle ABC with side lengths ABC. So when we name a triangle ABC, we are naming its vertices. We have the following formulas. Side A squared is equal to side B squared plus side C squared minus 2 times side B times side C times cosine of angle A. Then there's 2 other versions of this formula that basically isolate one of the sides. While these formulas look very complicated, they do follow a particular pattern. And I'm just looking at these formulas that involve isolating a side length. So if we're looking for a side length, that side length squared is equal to the other 2 side lengths squared and then added minus 2 times the product of those side lengths times cosine of the angle opposite the side we're looking for. I know that seems like a lot, but the more you use these formulas, you'll start recognizing these patterns. There are other versions of law of cosines that solve for cosine of a particular angle. So if we're looking for an angle rather than a side, we just manipulate these formulas to solve for cosine of that particular angle. Depending on what information is given to us and what we're looking for, we might use any of these versions of these formulas. Solve triangle ABC if angle A is 42.3 degrees, side B is 12.9 meters, and side C is 15.4 meters. So we're given 2 sides and the angle between those 2 sides. So side, angle, side. Similar to that last video with law of sines, I'm going to start by just trying to draw my angle. So angle A is 42.3 degrees. We're given side B is 12.9. It doesn't matter which of these legs you call B and which one you call C. I'm going to try to adjust the lengths to accommodate for the different measures. So I'm going to make the top side and side B. So this is going to be 12.9 meters. And I'm going to try to make then that base or side C a little bit longer. 15.4 meters. And then I can complete this triangle. So my lower angle is B, that top angle is C. We want to solve this triangle. We want to find the rest of these values. So I'm going to start by trying to find side length A. And I'm going to use that first version of our law of cosines that says side length A squared is equal to side length B squared plus side length C squared minus 2 times side lengths A, B times cosine of angle A. Now plugging in my values, side B was 12.9 squared plus C squared, which is 15.4 squared, minus 2 times 12.9 times 15.4 times cosine of 42.3 degrees. You're going to plug this all into your calculator all at once. We get that A squared is equal to some value 109.699, And I'm just using an ellipsis here to indicate that that value keeps on going, but I'm trying to record some work. But when I go to solve for a by taking the square root, I want to take the square root of that exact value. So I don't want to round that calculation for a squared and then take the square root where we will also round. That adds extra layers and it compounds that inaccuracy. That's the result of rounding. So taking the square root of that exact value and then rounding, we're going to get that a is equal to 10.5. Now that we have side A, that puts us in this situation of side-side angle. So we want to be cautious when it comes to using the law of sines. That note we had at the beginning, if we begin with law of cosines, we can complete the problem using law of cosines to avoid that ambiguous case. And again, the reason the ambiguous case comes up is because, well, when we have two possible triangles, inverse sine involved in law of sines is only going to give us an output of an angle between negative pi over 2 to pi over 2 or negative 90 degrees to 90 degrees. So if we continue using law of cosines, which will give us an angle measure from 0 to 180 degrees or 0 to pi, it allows us to solve for those obtuse angles without any issues. So let's go ahead and solve for angle C. And we're going to add some more notes to approaching these problems here in a minute. But without having that side length, we can't really address that comment quite yet. So we're going to solve for angle C next, and I'll explain in the next example why we're going to solve for angle C. So I'm going to use that formula that had cosine of angle C isolated. So remember, there are different versions of law of cosines. There's 6 different formulas altogether. Really I mean, if we think about it, we can learn one formula and then use that to derive all of the others. So it doesn't necessarily have to feel like quite that many, but having that access to them when we do, it is a little bit easier. So I'm going to use the formula cosine of angle C is equal to side length A squared plus side length B squared minus side length C squared divided by 2 times side A times side B. So now that I have all of my sides, I can plug those values into this formula. A is 10.5 plus B is 12.9 squared minus C is 15.4 squared, all divided by 2 times A, or 10.5, times B, 12.9. To find angle C, we're going to take inverse cosine of this expression. When we take inverse cosine of that expression, we do get that C is equal to 81.62 degrees. And now we can find angle B, taking 180 degrees minus the sum of those other two angles, so minus 42.3 plus 81.62. And just checking my calculations because the decimals get tricky. 56.08 degrees. In our next triangle, we're given all three side lengths. So side A is 9.47 feet, side B is 15.9 feet, and side C is 21.1 feet. So we're going to sketch this triangle. We want to try to be, again, as accurate as we can be with drawing those side lengths. That's a little trickier to do, but we can do our best. So 9.47. That's side length A, so angle A is going to be opposite that. Side B is 15.9. So angle B is opposite that, and C is 21.1 feet, so angle C is opposite that. For this example, what we're going to do is start by solving for the largest angle first. Okay. If you And the reason we're going to solve for that biggest angles first is basically to allow us to use law of sines later. If you're planning to use law of cosines for all of your calculations minus, finding the third unknown angle, then you don't need to worry about the order. But if you want to start using law of sines where that does introduce that opportunity for the ambiguous case, we want to make sure that we solve for the largest angle first to make sure it's not an obtuse triangle. So in order to figure out which angle is the largest in this picture, we want to look at our sides. If you recall from perhaps a geometry class, it is true that the largest side, the largest angle is opposite the longest side. Since we have all three sides, we can see that side C is the longest, which means angle C is going to be the largest, even though this picture doesn't really look like that. So we're going to solve for angle C using cosine of angle C is equal to A squared, so 9.47 squared, plus B squared, 15.9 squared, minus C squared, 21.1 squared, divided by 2 times A times B, or 2 times 9.47 times 15.9. To solve for C, we're going to use inverse cosine of this expression. And when we take inverse cosine of this, we find that angle C is equal to 109.94 degrees. Then we're going to solve for the next largest angle using, again, law of cosines, just to avoid any potential issue with using inverse sine. But we really could use law of sines because I do know that the next two angles have to be acute. How do I know that the next two angles are going to be acute? It's because B is obtuse. Since B is obtuse, almost 110 degrees, that means angle A and angle C need to add up to being about 70 degrees, right? Because all three angles need to add up to 180. So we actually could use law of sines, and law of sines is a little bit easier. So let's go ahead and do that. So let's find angle A. So we're going to do sine of angle A over its opposite side, 9.47, is equal to sine of 109.94 degrees divided by 15.9. So sine of angle A is equal to 9.47 times sine of 109.94 degrees divided by 15.9. And if we take inverse sine of this expression, sorry, I just caught an error that I made. It took me a while to figure it out. I've labeled this incorrectly. This angle C is 109.94. So I've set up my law of sines correctly. Sine of angle A over 9.47 equals sine of 109.94 degrees divided by 21.1. So sine of angle A is 9.47 times sine of 109.94 degrees divided by 21.1. Another reason why we got to be really careful. I think what I was looking at is angle B in my picture looked like it was the biggest and it looked obtuse. So that's why I labeled it with that obtuse angle. But my picture's obviously not very accurate. So just an example of being really careful. When things aren't quite adding up, sometimes it takes or it helps to just take a step back. So now that I've corrected my expression for sine of A, and we take inverse sine of that expression, we get that angle A is equal to 24.955 or 0.96 degrees. And then we can use my two angles that are given to find my third unknown angle, angle B, 180 minus the sum of 109.94 plus 24.96. We get that angle B is equal to 45.1 degrees. Airports A and B are 450 kilometers apart on an east-west line. A pilot flew from airport A to airport C. Then the pilot flew 350 kilometers on a bearing of 128 degrees 40 minutes to airport B. What is the distance from A to C? So we're going to start by setting up our picture. Since A and B are on an east-west line, we're just going to draw a horizontal and label A and B. And we know the distance between them is 450 kilometers. A pilot flew from A to C, and then from C, the pilot flew on a bearing of 128 degrees 40 minutes to B. So C is going to be somewhere above A and B between the two of them. Let's go ahead and convert this bearing. 128 degrees 40 minutes is equal to 128 plus 40 over 60. So this is 128.67 degrees in decimal degrees. So I'm going to sketch a line extending from A to C. And then I know that the bearing from C to B is about 130 degrees. I'm just going to use some even numbers just to kind of explain what my thought process is. 130 degrees is more than 90 degrees, but less than 180. So remember, when we're given just a bearing of degrees, we start at due north and we start measuring clockwise. So at this point C that I'm kind of making arbitrary, but keeping in mind that bearing, I'm going to draw my auxiliary compass just to help me set up my bearing. So 128.67 degrees, starting from that due north, will bring us down to that angle or that airport B. So this angle measure is 128.67 degrees. That's that bearing from C to B. Now what we're looking for is the distance from A to C. So using the vertices we've already named, A to C, that line segment AC is opposite angle B. So we're going to just call that side length B. We need some additional information about this triangle, though, in order to use any formula that we have. All we have currently is one side length. So we need, oh, I'm sorry. We also know that from C to B is 359 kilometers. So all we have are two side lengths. In order to use law of cosines, we at least need angle B. If we are going to use law of sines, we need angle A or angle C, which we don't have those. But we can use what we have already to find angle B. So inspecting that bearing of 128.67 degrees, that's starting at due north and then ending at that terminal side. Well, that 128.67 is the sum of two angles, a 90-degree angle and then something else. And that something else is what we want to look for. So this angle here is going to be equal to 128.67 minus 90, which gives us 38.67 degrees. That's from that, if I'm thinking about that auxiliary compass, that east line down to the bearing from C to B. Now, we also know that we have that east-west line on our bearing and the east-west line that A and B lie on, and those are parallel, which tells me that angle B is also 38.67 degrees because those are same side interior angles. We haven't referenced those in quite a while, but you could go back, I believe it was in, I'm not sure, maybe, probably unit 1. We reviewed those angle pairs formed by parallel lines and a transversal. So those are same side interior angles. And now looking at our picture, we have side angle side. We can find that opposite side B using our law of cosines. So B squared is equal to 450 squared plus 359 squared minus 2 times 450 times 359 times cosine of 38.67 degrees. Typing all this in our calculator, we get that B squared is equal to 79,118.19, so on and so forth. When we evaluate the square root, we want to use that exact number, not a rounded value. So taking the square root of that exact value, we get that B is equal to 281.28 kilometers. And this is an approximation because we are rounding at this last step, but we just want to make sure we don't round at multiple levels of our problem if we can avoid it.